Good morning or good afternoon, everyone. Thank you so much for joining us while we're all stuck at home on this international forum on research and development around environmental effects of MRE. My co-host here today is Jennifer Fox with Aquaterra, and this is the first of these forums. We're kicking this off with 3 webinars today, tomorrow, and the next day at the same time, and hopefully you've received information on all of those. This forum is sponsored by OES-Environmental and ORJIP Offshore Energy. Okay, just a quick note for those of you not familiar with OES-Environmental or ORJIP. Ocean Energy Systems, one of the International Energy Agency groups of interested countries, has a task looking at environmental effects. 15 of the OES nations have committed to this over this last 4-year period. This particular task is led by the U.S. The U.S. Department of Energy is the lead with the Bureau of Ocean Energy Management and the National Oceanic and Atmospheric Administration. We've been working in 4-year phases for a number of years now, about 10 years, and it is implemented by my laboratory, Pacific Northwest National Laboratory in the U.S. This phase will end next month in May, and we will be releasing the State of the Science Report, the 2020 State of the Science Report, which is an update from one written in 2016. That will be out in about a month, and I hope you'll look forward to, we'll do some webinars and other kinds of events as it was supposed to be released at a conference that isn't happening. So that's who we are. So Jen, do you want to say a few bits about ORJIP?
Sure, thanks Andrea. So for those of you who don't know, ORJIP Ocean Energy is the Offshore Renewables Joint Industry Program for Ocean Energy. It's a UK-wide collaborative program sponsored by different public agencies within the UK and has very well aligned aims and objectives as the OES-Environmental program, and we work very closely and collaboratively between our 2 teams. The Secretariat for ORJIP Ocean Energy is ourselves, Aquaterra, as well as 2 other organizations, one called Marine Space and also the European Marine Energy Centre, EMEC. And the overall aim of ORJIP Ocean Energy is to facilitate a strategic, coordinated and prioritized approach to the monitoring and research around the environmental impacts of ocean energy, ultimately to reduce the uncertainty around those environmental effects and to have some facilitated and prioritized research. And one of the key pieces of work that we do as part of ORJIP Ocean Energy is the Forward Look document. This is a document that presents a prioritized list of the key research gaps or knowledge gaps in relation to the key consenting risks of wave and tidal energy. We've done a couple of these of iterations of the Forward Look over the years that ORJIP has been in place, with the next version of the Forward Look, the most up-to-date version, coming this year in the next couple of months. So I'll leave it there, Andrea. Back to you.
Thank you. Okay, so why have we asked you here today? We have been discussing the idea of an international forum to really bring people in this community, the researchers, regulators, developers, and others up to date on a periodic basis. This started back in 2014, and we've never really gotten it together. So with us all sort of quarantined, this seemed like a great time. The purpose of this forum is really to showcase up-to-date understandings of what we know about environmental effects around marine renewable devices from research and development around the world. We want to demonstrate what advances have been made in monitoring. Most of these advances have come through research projects, and the idea is to be able to apply them to monitoring both before, during, and after operation of devices in the water. This is an opportunity, we believe, to provide sort of access to the researchers and the monitoring leads who are really at the forefront of what's going on in terms of acquiring data, information, and knowledge around these devices. And also, the hope is that we will get a better handle as an audience of regulators, developers, researchers come together on these forums to understand what those real interests and needs are, both for consenting, permitting purposes, but also to really move the science forward. So we're starting this off with 3 days of webinars. Today's is on updates of monitoring research around turbines that are actually deployed in the water. Tomorrow's forum will focus on some of the integrated monitoring platforms that are in use or in development for monitoring around devices. And on Thursday, we'll do an update on the monitoring and research going on around wave devices. So that's kind of where we are now. So I'm going to pass this back to Jen to just go into the speakers and what you'll hear for these next 3 days. So there you go, Jen, for today.
Thanks, Andrea. So as Andrea said, today's webinar will focus on monitoring research around operational turbines. So we've got 5 speakers today. Our first speaker is Doug Gillespie from the Sea Mammal Research Unit, and he's going to be talking about some work that they've been doing around the Maygen project here in Scotland. We're then going to have Kate Smith talking about Nova Innovations deployment. And then we're going to have Craig Chandler from Sustainable Marine Energy, or SME, talking about their deployment. The 4th speaker there is Diane Gomez from Sabella, and our 5th speaker will be Gemma Veneruso from Bangor University talking about Minesto's deployment in Wales.
So, yeah, so my name is Douglas Gillespie. I work at the Sea Mammal Research Unit at the University of St Andrews in Scotland. These are some slides I put together with Fraser Johnson, who's one of the engineers, or as far as I'm concerned, the chief engineer at the Maygen project, which is run by CMAC Atlantis Energy. If you're confused about the names of these companies, please ask Fraser, not me. This work would certainly not have been possible without the input of many people at CMAC Atlantis, and also many of my colleagues at the Sea Mammal Research Unit have all contributed vast amounts to this research. So just looking at the timeline of things, or perhaps even starting with where we are in Scotland, is the project's right up on the north coast. So if you're in Orkney, it's to the south. The rest of it is probably north of where we are. And as the tide comes in each day, it's forced between the Orkney Islands, that's those little islands above the north of the red arrow there, and then mainland Scotland. And there's also a wee island in there called Stromer Island that you can see in one of the middle pictures behind the green crane. And the water's forced through there at about 10 knots speed. So there's an awful lot of energy to be extracted. You can see the timeline at the top of this slide. CMAC Atlantis were talking to regulators and people at least a decade ago. Looking back through my emails, our first contact with the engineers and serious conversations about what types of environmental monitoring to put in place started in about 2014. But the exciting stuff really started to happen in October 2016, when the turbine support structures and our monitoring equipment went into the water. So there are currently 4 turbines deployed in the Maygen array. They're horizontal axis turbines, and they're currently spread out with about 200 meters between each turbine. They're gravity mounted on sort of quite large tripod structures, and they're about 38 meters of water. And as I said, it's a 10-knot current, so there's plenty of energy there. So each turbine can kick out about 1.5 megawatts of power. A 9-meter blade radius, and you can see photos of them here. They look like a kind of short, tough wind turbine mounted on the seafloor. They can rotate at maximum speeds of up to 20 RPM, but 14 is more typical for maximum power yield. And Maygen or CMAC Atlantis have future plans, which I'll talk about later, to scale up to 86 megawatts, and I believe that their licensing consent potentially allows for up to nearly 200 megawatts. Again, you can see at the top of this slide, they've been very successful at generating power. It was a bit up and down over the first year or so, as anyone would expect, but they're now regularly outputting well over gigawatt hour a month to the national grid, and they've made a total, I believe, of over 28 gigawatt hours of electricity now, which we've all been using in the UK for useful things like boiling kettles, making PowerPoint presentations to show at conferences. So in the phase 1A, that's the 4-turbine array environmental monitoring, which is really designed to understand the movements and behavior of animals around a small number of turbines before they scale up to the larger arrays. We have 5 types of sensor deployed, and I know you can see 4 on the list. There is another one, don't worry, I can't count. First of all, we have passive acoustic hydrophones for monitoring small cetaceans, and these were mounted on the foundation of the tidal turbine. We also had cameras. There may be a video coming up, which is of our connector plugged in. These were also mounted on the base of the on the foundations of the turbine. Now, a multi-beam active sonar, which was deployed on a bracket hanging off the side of the turbine, but then craned away to a location about 30 meters away to look back at the turbine. Then there was the flowback system from the University of Aberdeen, which Benjamin Williamson and Bev Scott will be talking about more tomorrow. So I'll spare you any details on that. Again, that was deployed on the side of the turbine so it could be cabled in on the shore and then lifted to its final resting place. And finally, the fifth sensor that was deployed was GPS tags on the local harbour seal population. And actually, of all the marine mammals in the vicinity of these turbines, it's harbour seals which are potentially of greatest concern due to the decline in numbers of harbour seals in recent years. So I'll start with the seal tagging results, and this is definitely the one bit of work that I've had no input to whatsoever. It's primarily the work of Joe Onofrio, who recently completed his PhD with us at the Sea Mammal Research Unit. And his work showed that seal distribution, as many would expect, is primarily driven by tidal dynamics. The seal distribution did not change with the installation of the turbines, so the installation of the foundations and stationary turbines had no effect, or no measurable effect, on seal distribution. But when the turbines started to operate, there was a change in the distribution of the seals. If you look at the diagram, you can see Stromer Island there, and the turbines, I don't know how clearly you can see them, there's 4 little boxes drawn to the south of Stromer Island, and those are the locations of the 4 turbines, and those little minus signs and little plus signs to the northwest indicate that the seal density in those areas went down or up while the turbines were operating. The Joe concluded that seals are actively avoiding the turbines when they're operating, but that they do continue to use that site during non-operational periods. They concluded also that overall the movement behaviour does not appear to be hindered by the presence of the turbines, suggesting that pre-installation foraging sites, which are of course what's important to the animals, have not been significantly obstructed. There's a couple of papers due to be out to be soon, we hope, on Joe's work. First one, I haven't talked about here, it's a fantastic paper looking at the empirical determination of trauma in seals from collision with turbine blades, where basically Joe and colleagues strapped a thing that looked like a turbine blade to the front of one of our workboats and drove it at seal carcasses and looked at which point the bone started to break. So I recommend you read that. And Joe assures me that they're about to submit a paper on the distribution data of seals around tidal arrays that I've been describing here. Moving on to the other sensors that were integrated more into the turbine, it was a mixed bag of performance results, really. But first of all, as I say, this stuff was put in the water in October 2016. And between October 2016 and October 2017, there were some power problems with the power supply that we get from the turbine to run our system, and we were unable to collect data. This was rectified in October 2017 after the turbine had been out for some other maintenance, but unfortunately there were continued problems with the power supply to the flowback platform, which again Benjamin can talk about tomorrow, but we did have power to our other systems. However, we found that in that year's period, our multi-beam sonars and our camera equipment, or the connectors to that equipment, had corroded and failed. So we were also not able to collect any data from the multi-beam and cameras. So we did recover those sensors, and it looks like we would have probably got a few months of data out of them before the corrosion was cut. The passive acoustic system, however, did operate successfully from October 2017 until October 2019 when it was decommissioned. So we had nearly 2 years of PAM data. And again, you can just see everyone knows what your equipment looks like when it goes in, all nice and shiny, and what it looks like a couple of years later when it comes back out. So I'll talk more about the PAM system in detail, because that's the bit we've got data from. As I said, it was mounted directly onto the turbine foundation. Hydrophones, we mounted them in 3 tetrahedral clusters. You can see one of those on the bottom left, in the bottom left picture. These were protected by polyethylene hard hats, which may not be acoustically perfect, but they did protect them in what's an extremely harsh environment. And the fact was free stuff, I think is testament to the importance of that. They have a high 500 kilohertz sample rate, so that we detect the high frequency sounds of porpoises. And all the data was digitized in with a national instrument system we developed mounted in a junction box close to the hydrophones and then streamed to shore via Ethernet where it was processed in real time with the PAMGuard software. We also developed an additional watchdog program to keep PAMGuard running should there be a power outage either at the substation or the software all over for any reason, which ensured 24/7 operation. And over the 2 years of operation, when power was available to us from the turbine, we achieved 99% reliability. Data were then validated offline at the lab and clicks localized using time of arrival methods of the different hydrophones. Going through the PAM results, and I should tell you that I'm sure a lot of you are aware that the EIMR conference is on this week in Scotland. For those of you who weren't planning to come, I'm sure you'll be unsurprised to know that that conference is not happening in person, but a lot of these presentations are online there. There's a couple of presentations, one by myself and one by my colleague Laura Palmer, which give these results in quite a lot more detail on the EIMR website. So over the 2 years of monitoring, we had 1,516 logged porpoise encounters. That's when we looked at the click waveforms and spectrums of, yes, that is a porpoise going by. And many of those we now have more than one animal. You can see the daily counts of porpoises, or month average daily counts of porpoises for the first year of operation. Again, you can see that there's a strong seasonal variation with many, many more animals being present in summer than in winter. The more detailed modelling that my colleague Laura Palmer conducted also shows that animals are much more likely to be present at night in most seasons of the year. So one of the things that tells us is that season surveys in summer are probably actually quite a poor way of estimating overall risk. In this case, the summer daytime survey would have vastly underestimated the number of porpoises likely to interact with the turbine. Of course, in other situations, you might get an overestimate. But the real interesting result from Laura's analysis was that porpoises are less likely to be present when the turbine is operating. So the bottom right plot shows the change in porpoise presence during turbine operation. Shows that high flow speeds of around 3 knots, you can get up to a 78% reduction in porpoise presence compared to when the turbine is not operating. We've also been looking at the fine-scale tracks of individual animals, and in 541 days of fully processed data, then had a single harbour porpoise that actually passed through the rotors. When this happened, the rotors were actually stationary. It wasn't a flood tide. The tidal flow was 2.8 metres per second at the time, but the rotor blades were stationary at the time. We've had several animals passing quite close to the rotors while they were operating, but none obviously going through the turbine. And we've got clear tracks above the turbine, below the turbine, and to the side of the turbine, as you can see in some of these other images here. But there were also a lot of cases when it was very unclear what was going on. There were kind of clicks all over the place, possibly more than one animal present, and it was very difficult to determine exactly what the track of the animal was in those situations. We've also been looking at just the spatial distribution of localized clicks around the turbine. And these plots are a view straight into the turbine, starting between 30 and 25 meters in front of the turbine and working our way through to 25 to 30 meters behind the turbine. These little two plots that you can see here are the distributions of clicks around the turbine, up to 5 meters in front of it and 5 meters behind it, with the yellow dots while the turbine is operating and the purple dots while the rotors are not operating. And again, I think you can see that there's a clear avoidance of clicks of the actual turbine rotor area, which is, of course, the sort of fuzzy brown disk, and that there's also potentially seems to be an aggregation of clicks close to the foundation of the turbine. And these results are confirmed by the statistical analysis of these data. So just to summarize, we successfully ran a PAM monitoring system at an operational turbine for a 2-year period. We found strong seasonal variation in rates of animal encounter over that time. There was a reduction in porpoise presence when the turbine was operating. There's also evidence that there's a fine-scale harbour porpoise avoidance of the immediate vicinity of the turbine rotors. There's also evidence that seals are reducing their usage of the area when turbines are operating. The number of papers which are either published and just submitted or kind of half-written. There's 2 papers describing the technical aspects of the system, how it works, how some of the algorithms work, how we put it together. There's a paper which was submitted yesterday describing the temporal and tidal turbine operation-based presence of harbour porpoises close to the turbine. And then there'll be a paper submitted shortly, we hope, on the fine-scale distribution and movement of animals around the turbine. There's also an excellent paper by Denise Riche, which again you can see a presentation of this at the CINR conference website, where she characterised the underwater noise of the turbine and drifting hydrophone receivers. And she basically showed that, I think the take-home message from that paper, there is no way that a porpoise or a seal could go past that turbine while it's operating and not be able to hear that it's there. Of course, Major have got grand plans for the future. As I said earlier, they're planning on scaling up to an 86-megawatt array in the coming years, and potentially they might even go beyond that. And one of the things that our engineers are most interested in at the moment is, apart from how to work while we're all in lockdown, is exactly how they're going to position the turbines relative to each other. And if you look at these plots, you can see they're looking at 16-metre spacing between the turbines, and potentially as little as a 4-metre spacing between the turbines. And this, as people are interested in the environmental effects of the turbines, raises quite a number of questions for us. First of all, we've got no information at all on the fine-scale movement of seals close to a rotating turbine. But for the porpoises, we still don't know how any of the animals are going to respond to an array of turbines. Will they just leave the area completely? Will they try to move between the turbines? We don't know, and it may be impossible to find out until there is an array in place. Because although they seem to avoid one turbine, will they be able to pass safely between many closely spaced turbines? Or will they be excluded from the entire area? We don't know. So this work was funded by the Scottish Government, and we're very grateful to them for that funding over the years. As I said, many co-workers at the Sea Mammal Research Unit have put enormous amounts of work into this project, many of them much more than I have, and it would have been impossible without the engineering team at CNEC Atlantis, who enabled the project and went to vast efforts to make sure that the environmental equipment was successfully integrated into their system. And the Scottish Government have got a very active steering group who remind us of why we're doing this work and what are the parameters they really want us to measure. And again, a lot of thanks should go to people at the University of Aberdeen and their system. All of the software that we developed, PanGuard, and the software for driving our acquisition systems, all open source and freely available. And I'd also recommend that you listen to tomorrow's presentation by Gordon Hasty, who will tell you much more about what we're planning next.
Thanks, Doug. That was great. I will pass on a question. There was one question there from Dan Hasselman, a simple question. Are the plots on these slides available in a publication?
Not yet, but I'm working on it. If I wasn't on this call, that's what I would be doing now.
Great. Yeah, I think it was slides 9 through 11 that Dan was asking about.
So some of these slides are available, okay, if you want to look at them, and on the EIMR website, but they haven't been written up as a paper to a journal yet.
Okay, great. So there's another question here. It's saying it's encouraging to see porpoises are generally avoiding the turbines, but did the monitoring systems have any impact detection capability?
Did the monitoring systems have any impact detection capability? No, is the answer to that. I think there's no way we would have, I don't know what we'd try to detect, if it would be a thud, a squeal. I think the answer is
yes. Great. Okay, wonderful. Well, I think we're going to have to move on. That was really a great presentation, Doug, and we'll look forward to hearing what Gordon has to say tomorrow.
Hi there, I'm Craig Chandler with Sustainable Marine Energy. I'm going to give an overview of the environmental monitoring results so far at SME's deployment of the plate-eye technology at Grand Passage in Nova Scotia. So thank you all for tuning in today. I'm their SME's compliance manager, so I deal with permitting and coordinating the environmental monitoring program. So briefly about Sustainable Marine Energy, they're a tidal energy technology developer founded in 2012. with the objective of developing tidal energy systems to provide island and coastal communities with a source of reliable and predictable clean energy. SME has locations in Edinburgh, Scotland, in Germany, and in Halifax, Canada, where I'm based. The Grand Passage demonstration project, as well as being an ongoing testing ground and later this year, the plan is to grid connect the existing there, so it will be generating power to the grid. Besides that role, it's also being used to, on an ongoing basis, develop the technologies and particularly in the short term to test devices for deployment at the Force site in the Bay of Fundy. I'll give you a quick picture of the Grand Passage location. It's in the circle there. It's a narrow passage between the Bay of Fundy, the outer Bay of Fundy, and St. Mary's Bay in the western end of Nova Scotia. There are strong currents there that promote mixing and scouring of the seabed with depths ranging from about 12 to 30 meters. And maximum current speeds around 3 meters per second. The tidal range there is over 6 meters, but of course at the Force site and other locations of the Bay of Fundy, it's much larger than that. And the bottom image shows the location of plate high in the main channel of the passage. And this is the same plate high device, by the way, that was deployed in Connell, Scotland in 2018. As far as the habitat, Grand Passage has significant marine animal diversity and abundance, but it's not considered critical habitat for marine mammals. The fish at the Grand Passage are expected to be similar to those in the adjacent areas of the Bay of Fundy and St. Mary's Bay, so there's a lot of similar habitat in the area. I've listed some of the typical animals seen in Grand Passage with the note that the whales, the large whales, are infrequent visitors that tend to just transit through the Grand Passage. So the objectives of the monitoring program, which began early last year, by the way. So the results I'm talking about today are from 20 projects. We want to, of course, observe what animals are doing. And the next couple of slides, I'll talk about what sensors are being used in particular. Want to collect data to allow us to better understand what the marine animals are doing in the wider area and allow us to evaluate the risk associated with potential interactions. And as Kate was saying, the concern here is the same, that it's mainly a focus on collision risk. We also want to identify future data needs and continually evolve the program to meet those needs. And as well as Grand Passage being a testing ground for the power conversion equipment and the system as a whole, we also have a focus on adapting and developing an environmental monitoring system that can be used at Force, where we won't be able to rely on optical cameras. So this diagram shows the location of the sensors that we're using for the regulatory mandated part of the environmental monitoring. 4 cameras, each focused on a turbine rotor. So the plate high, for those not familiar, has this version has 4 6.3 meter diameter rotors. There's a camera mounted on the deck and a hydrophone mounted on the port, the leading edge of the port pontoon. In particular, I mentioned the we're using McCartney underwater cameras and ocean sonic side seedless and hydrophone. In addition to that, we're doing marine animal monitoring every 30 minutes during turbine operation. The technicians have been trained to conduct this work, and I'll talk about the results of that in a little bit. The last point there is that for the current testing program, we're required to stop the turbines, which can be done remotely using their braking system, if species at risk or unidentified baleen whale are seen within 100 meters of the device, and that has not occurred to date. This, if things work properly, should be seeing a turbine spinning. So this is a sample of the underwater video data we're collecting. This is a better quality image, but it shows that typically, especially last spring, the water quality allowed us to make good observations. Aquaterra is reviewing that data for us and correlating it with the time of day and the flow velocity and direction and the tidal cycle. And so far, the regulator has found the video quality acceptable, and it's been appropriate for our uses. This should be showing you another video where the water quality is not quite as good, and it is on a loop, so you'll see a fish go by. It's not a parade of fish, but it just shows that the water quality is variable in the area. That is the only fish that we have positively identified in the video that's been reviewed. There have been many jellyfish, and as you can also see in that photo, a lot of other debris at different times, particularly after storms. And this is just due to the natural environment and water quality. No contact between marine animals and the turbines has been observed, and no other observations of animals near the turbines. So we're currently working with FORCE and the Offshore Energy Research Association in Nova Scotia on their Pathway project, and that's part of our work to developing the environmental monitoring system for FORCE. Moving on to the hydrophone data results. We're using JASCO Applied Sciences, who, in addition to being international experts in underwater sound, they're also very familiar with the Bay of Fundy conditions. We've had good results collecting data through 2019. We did see, as expected, that the turbulent flow and the high velocity flow around the hydrophone and the platform does cause interference noise, but between the two testing programs in 2019, we adjusted the location of the hydrophone and had a significant improvement. But overall, the data has served the purposes that we need it for in the environmental monitoring program. The graph on the right shows the regular, the red lumps at the bottom are the low frequency sounds generated by the tidal flow, and you can see that through the frequency ranges, and that's just the natural flow. And then you'll see a band in the middle with a bunch of other noise, especially in the higher frequency ranges and on either end of the graph, and these are the periods of turbine operation. So they're definitely, as expected, it's picking up the noise from the turbines. We also have some horizontal bands near the top, particularly at the 20 kilohertz range, where we're picking up some electronic noise. This is an example over 3 days in fall of 2019. And we've worked through that problem. We think we have that resolved now, although that 20 kilohertz interference wasn't causing the data was still useful for our purposes, and we could extract the information we need, which I'll speak about in the next slide. So some of the results, JASCO indicated that the worst case measured sound levels to date would be well below the sound levels generated by a typical vessel in Grand Passage, such as a fishing boat. They also applied a couple of different automated analysis to the data, including moan and whistle detectors, looking for baleen whales and dolphin sounds. The automatic detection detectors identified a lot of potential signals, but a manual review of a portion of them did not identify any actual baleen whale or dolphin sounds. And this wasn't a surprise because of their infrequent passage through the Grand Passage. Porpoises, on the other hand, again, there were quite a number of false positives. So, for instance, in the manually validated information, about 1 out of 5 was an actual porpoise click, and the rest were false positives. And the graphs on the right are just samples of that data, the automated detections and the validated ones. JASCO determined that it was highly unlikely that porpoises, due to the sound levels generated by the turbines, even if they remain near the plate height for an entire day, that there would be any injury. And similarly for fish, neither hearing injury or behavioral disturbance is expected. Marine animal observation, and this would be people looking out on the water, similar to what NOVA's doing in Shetland, was conducted at 30-minute intervals during operating periods of the turbine. For the first testing program in the spring of 2019, this was a regulatory requirement, but it was not for fall, but we continue to do that to collect that data and potentially correlate it to other environmental observations. The Inspire Consultants from Nova Scotia has been assisting SME with developing that program and providing third-party review. And there have been very few observations in the vicinity of plate high through the testing programs. There have been some porpoise and I think 2 separate observations of seals and cormorants. And this goes along with what local residents and fishers indicate, that that's not uncommon for the central part of the passage to not see many animals. So just to wrap up, SME's next step with the Grand Passage project, as I said, we're going to continue to operate that platform there and collect environmental data, and along with that, continue to develop the environmental monitoring system that will be used at Force. Right now, we're limited to daylight operations. We want to move to 24-hour operation. And late this year, the plan is to install the 2nd-generation plate high device for testing at Grand Passage prior to its installation at Force. We also want to, as we go around talking to people, make it known that we're very open to sharing the data that we have with researchers. And right now, the Bryden Center is using some of the hydrophone data in their biofouling research. So that's what I had to tell you about today. Thank you very much.
So hello everybody, I'm Diane Domé, project manager at Sabela. So I will tell you a bit about the environmental monitoring we do on our projects, and especially on our Sabela Ditten project, which is our flagship project in France. So just a few words about the project so that you understand the context. So the project is located in the Frondeur Passage, which is near Ushant Island, which is an island west of France. It's an island with 900 inhabitants all year round and much more during the summer. It's an off-grid island. It's not connected to the mainland. So the electricity is produced with diesel power gensets with electricity consumption that change a lot during the year, and they burn around 2 million liters of fuel per year to produce their electricity. So it's really interesting to produce clean electricity for this island. On the two photos below, you can see where one of the only sand beaches on the island where our cable arrives and where the front-door passage is located. So this project, the goal was to install and connect the first full-scale tidal turbine in France. So it's a 1 megawatt device that has a 10-meter rotor diameter. And there have been 3 operation periods for the moment. So the turbine was initially installed in 2015 for 1 year because we initially got authorizations for a 1-year demonstration. Then we asked for prolongation of this authorization. We put back the turbine in water in 2018 for 6 months. Then we retrieved it for small maintenance, and now we are going to put it back in the water as soon as we can because with the current situation it's impossible. But hopefully we will put it soon. And it will stay in water until 2022 when we will install a first pilot plant with 2 bigger turbines that will be commercial turbines and will stay for 25 years. So it's installed in the front-door passage and it's connected. It's been connected since the beginning in 2015 to Ocean Island network and injecting electricity there. So that's a photo of the turbine before installation. So it's 10-meter diameter rotor. 17 meters high, and yeah, it's put on a gravity-based foundation of 20 by 20 meters for a total of around 400 tons, a total weight of 400 tons, and the rotation speed is quite low. Is between 5 and 15 runs per minute, depending on the undercurrent velocity. The front-door passage is where the turbine is installed. The depth is 55 meters. We are located 2 kilometers from the shore of Ocean Island, and the current velocity can be up to 4.5 meters per second. What is interesting is that it's a highly environmentally protected area with many environmental protection layers, important bird area, natural zone of ecological interest, UNESCO biosphere, Natura 2000 site, and I will not mention all of them because there are really many layers, and it's part of the Marine Nature Park of Iroise Sea, who is managing what is called the Iroise Sea, that is west of Brittany in France, and especially looking at the environmental preservation of this sea. And in addition to that, it's an area with many human activities, fishing, professional and leisure fishing, diving activities, sailing, navigation. There are ferries going from France and UK to Spain, military vessel, etc. So we got the authorization to install 1 turbine, and hopefully now we will get the authorization for the pilot farm. But the condition was to have a high environmental monitoring around the turbine and to go step by step, monitor the impact of 1 turbine, then of the pilot farm, and then maybe it will be possible to go to a wider, a bigger farm and a bigger commercial farm. So we developed an environmental monitoring protocol in close collaboration with the Iroise Marine National Park, who told us what they wanted us to monitor. And then we integrated several instruments on the turbine and on separate structures that are either connected to the turbine or autonomous. The main aspects we were asked to focus on are the acoustic impacts of the turbine, and especially the acoustic impacts on marine mammals. So for this, we installed hydrophones, CPODs, which are kind of hydrophones that are dedicated to marine mammals recordings. Surface and also surface measurements from a surface vessel, either with the turbine or without the turbine to see the difference. We also made some numerical modeling for the acoustic impacts because it's complementary to the measurements. Then the second important point is the collision risk. Collision with marine mammals, with fishes, but also with diving birds that are quite frequent in the area. So for this, we use mainly video cameras. Then the third point is biofouling development. So for this, we do survey with divers. We collect samples when we recover the turbines. Yeah, that's mainly how we do focus on that. And then the last point is impacts on currents and turbulence, but also on sediment transportation. And for this, we use different kind of ADCPs and also numerical models because sediment transportation is quite difficult to measure in this area. So that's a summary of what we have on and around the turbine. So on the turbine, so we have several ADCPs on the turbine that look at different directions and different kind of ADCPs that don't measure exactly the same way. We also have some fouling squares to control the fouling in a scientific way. So we have this kind of squares at different locations on the turbine in order to see the development of biofouling depending on on the exposition to the current and to see if there are any difference depending on where it is located on the turbine. On the turbine, we also have corrosion sensors to monitor the corrosion. On the gravity-based foundation, we also have some fouling plates that are oriented in different directions. And as the gravity-based foundation has remained in the water since 2015, we will have a really good overview, and we will really be able to see the evolution of this with time. And finally, directly on the turbine, we have a video camera, a swell sensor, and a speedo. So the video camera is, I will show you photos from this camera after, but it's behind the rotor, so we can see half of the rotor rotating, and it's a security because it's always connected to the turbine. So we are sure that this one is always working. Because then we have an autonomous structure, the one you can see on the right. This structure is located on the seabed, just a bit front of the rotor. And on this structure, we have several cameras looking at the rotor and looking at the seabed. We have a hydrophone and we have a CPOD to monitor the marine mammals. And then finally, we also have two other ADCPs that are located on both sides of the turbine, a few 10 meters. And these ADCPs can either be autonomous or can be connected to the turbine when the turbine is installed. So they're connected by divers, and like this, we maximize the chance of collecting information, and we maximize the quantity of data we can get. So these ADCPs are on both sides of the turbine to see if there is any impact on the flow, on the current, and on the turbulence, and also to assess the power curve of the turbine. So on these pictures, we can see some images from the video camera that is located on the turbine with blades on some of the photos. I didn't put a video because I was not sure it would be working. So, but in any case, you will not have seen the rotor rotating because what we have observed is that we can see fishes coming around the turbine only during the tide flags, which means when the rotor is stopped. And whether the turbine is there and the turbine is rotating or not, it's the same. The fishes come only when the current stops. And as soon as the current velocity starts to increase, the fishes go away. So we only see a few fishes during tight slacks, and it's not at each slack. It's really one fish sometimes, and it's not. There is really not so much life in this area, and this is what we expected. Is that the current is so high that there are only some kind of species that come here, and they don't come at all times. They only come during the slacks. And we've never seen, even if they are in the area, we've never observed a dolphin or porpoise or any marine mammals close to the water. And finally, I will just tell a few words about the environmental impacts of the cable, because this is something we were not focusing on at all at the beginning. So now we are participating in a project that is managed by France Energy Marine in order to assess the environmental impacts on the cables. So as part of this project, there are regular diving on our submarine cables, but also on control cables where there is no electricity passing, in order to see if there is, to monitor the development of biofouling on the cable, and to see if there is any difference when there is electricity passing the cable or not. And then finally, there will be electromagnetic measurements nearby the cable, which are planned to happen when the turbine is reinstalled, hopefully in the next few weeks or months. All right, thank you very much for your attention, and if you have any questions, don't hesitate.
Great, thanks. So the Cetaceans project at the university has developed a research and development project with Monesto to investigate cetacean response to an operational paracite. This project was part funded by the European Regional Development Fund issued by the Welsh Government, part funded by Bangor University, with investment from Monesto, and the CMAMO Research Unit was consulted for guidance and expertise. Great. So the study site is based in the north of Wales in the UK, in a body of water known as the Holy Head. And that's approximately 7 kilometers from shore and is about 85 meters in depth. It experiences mean peak current flows of 1.5 to 2 meters per second. And it is here that Monesto has commissioned the DG500, which is the first utility-scale paracite. It has a rated power of 500 kilowatts and a 12-meter wingspan, and they successfully conducted offshore commissioning and testing in 2018 and 2019. They've been awarded further funds for the next phases of development, which include installing an additional system, increasing capacity, and planning for an 80-megawatt array. We also have a number of cetaceans that use the area, and we're primarily interested in the bottlenose dolphin and harbour porpoise, for which there are a number of special areas of conservation dedicated to the species, either within or nearby the development zone. The bottlenose dolphin is a semi-resident population with a known home range of at least from Cardigan Bay and the Southern Bay in Wales up to the Isle of Man. And current abundance estimates suggest there's a population size of 200 to 300 individuals. So we expect the encounter rates are quite low for the area, but the low population count does mean that they are potentially vulnerable to population level effects. The harbour porpoise is the most common species in the area, and current abundance estimates estimate 15,000 animals for the Celtic and Irish Sea, and local density estimates of 1 animal per square kilometre. But we have no site-specific encounter rates for the Holyhead Deep in particular. Records show that there are also occasional encounters with common dolphin, rhesus dolphin, and minke in the Holyhead Deep. So there were a number of incentives to build this project. The DG 500 marine license had a condition to monitor potential collision risk between Cetaceans and the kite during operation. We still have fairly limited knowledge of collision risk with tidal stream technology. We have no knowledge of underwater behavior around tidal kite or an established system to monitor a tidal kite. And to our knowledge, there are no published studies of dolphin response around tidal technology. So using passive acoustics to track cetaceans around tidal turbines has been done before. We heard from Doug earlier, who's currently working on the Maygen project to track cetaceans, and also worked on the Delta Stream project in Ramsey Sound. And the concept is that multiple hydrophones are arranged in arrays, and they detect cetaceans as they produce echolocation clicks. And as an animal moves through an area, the difference between the time of arrival of clicks on those hydrophones allows us to calculate animal position and track their movements in 2D. So with that in mind, the project objectives were to use a similar approach to develop a customized passive acoustic array that would localize cetacean vocalization around the monastic kite and to investigate dolphin and harbor porpoise movement around the kite to assess the potential collision risk. The kite is tethered to the seabed and the current flow lifts it so that it flies in a figure of 8 at several times the current speed. And here is just a top-down schematic of that kite site. And we're interested in whether animals swim into that area covering the flight path. So for this study, we were focused on monitoring the ebb tide, and we wanted to install 2 clusters of 4 hydrophones, or we call them 4 channels sometimes, directly underneath the predominant flight path of the kite so that we could track echolocation for quick change on the ebb tide. So each 4-channel cluster would allow us to calculate a bearing, and where those 2 bearings would cross would give us an animal's position. We also wanted to install a single-channel array so that we could monitor detections on the NIST scale. We had a number of trade-offs to consider when designing the project. We had no power from the kite or from shore, so we were going to have to rely on batteries. And we also had no real-time data feed or data offload system, so we were data stores limited as well. This means that we'd have no choice but to have a high turnover of deployment. And in terms of budget and feasibility, that means we needed a small vessel and subsequently small mooring. So for the multi-channel array, or the clusters, we used sonar point recorders that were built by Desert Star Systems. These are advertised at 56 to 71 day endurance. They have an internal battery pack and 4 terabytes of SD card storage. We chose to continuously sample at 312 kilohertz. It had a built-in GPS clock and we produced WAV files. There were a number of customizations to the instrument made specifically for our project. The hydrophones were moved external to the recorder and arranged in a 15-centimeter tetrahedral array. Harness cables were produced and they would connect 4 recorders together. And 1 recorder was configured as a master and would send recording instructions to the others, and it would also provide a single clock for all connected recorders. For the single channel array, we used off-the-shelf sound traps, and we set those at a 50% duty cycle by 1 device that had a larger storage capacity, sampling at 96 kilohertz with the high-frequency clip detector turned on and an external battery pack attached. Our field plan was to conduct a 1-day sea trial to test the cluster functionality and then deploy the 2 clusters prior to kite installation. We wanted to do monthly deployment and recovery using a local boat charter, and we had spare batteries and SD cards so that we could swap out at sea, and we planned for a 1 to 2 day turnover of instrumentation. The sound traps were to be deployed 500 to 800 meters from the DG 500, and then configuration so that they would surround the kite, but also be a safe enough distance from other instrumentation and mooring lines that were at the site. We used chartered a 13-meter mooring service vessel for this job that had a marine crane and a 25 square meter deck face. And we used a gravity-weighted deployment hook to lower the frame to the seabed so we could have a more accurate position placement of moorings. We used single point moorings so that they were easier to manage in small vessels and so that there was no risk of entanglement with existing gear on the seabed. and these would be brought back up to the surface using acoustic release. Actually, in practice, when it came to deploy the clusters just prior to the kite installation, we had access to Minesto's charter vessel, so the array was deployed using a shift in dynamic positioning for that one deployment, but that wasn't the plan for the duration of the project. Knowing the precise locations of each hydrophone position from the seabed is crucial for accurate localization. And we had two methods to do this. Stage one was using pinger trials to determine the location of the hydrophones on the seabed, as well as the pitch, roll, and yaw, and to assess bearing accuracy. And this was conducted as soon as possible after deployment and again before recovery. And we would send chirp, porpoise-like signals and sine waves played with a transducer over the side of the vessel whilst logging GPS position. And the boat would drift over the acoustic array at varied distances and bearings, and we would later collect the acoustic data on recovery of the array. We also attached a sea tag to our cluster moorings that were also built by Desert Star. They contained a magnetometer and an accelerometer, and that would help us determine orientation of the array and also detect any movement of the mooring frame. So some preliminary results. We deployed the multi-channel array of clusters on the 9th of August 2019 and recovered them on the 21st of September. And we deployed the sound traps on the 27th of August 2019 and recovered on the 2nd of December. Unfortunately, we were not able to localize Cetaceans to position on this deployment as we had some issues with frame movement on the large spring tides, some intermittent sync issues within clusters, and some multi-ingress in some cluster 2 recorders due to connector corrosion, which affected the functionality of some channels. However, we did collect data and lots of it. We collected 31 days, totaling 200 amongst all recorders, and that's excluding the sound traps, which are still to be analyzed. And that came to 11 terabytes of data. And we were expecting to generate huge volumes of data, so it was really critical that we had IT support from the university, from the ISEC as part of the project planning, and I can't emphasize that enough. As Kate mentioned earlier, you generate huge amounts of data, and in that project planning phase, having a set of methods to cope with those data volumes is critical. So each partner held one hard copy, and we had a copy on the cloud. We had lots and lots of hard drives for processing, and a high processor PC dedicated to working with this data only. The raw data channels were merged using custom software, and processing occurred in Vanguard, and it took approximately 2 days to run each cluster. The process data was about 100 gigabytes per cluster. And we detected moderate rates of dolphins. We had bottlenose common dolphin quick trains, or common dolphin quick trains, and high rates of rufous dolphin quick trains. We also detected harbor porpoise, but that data has not been processed yet. Here's a screen grab from Vanguard. Sorry, it's a bit fuzzy. But in the top plot, we have bearing on the Y and time on the X. And here is a screen grab of cluster 1 showing successful bearings of quick trains. And yes, I mentioned bearings on the Y-axis. And the colors are manually marked out rufous dolphin quick trains. And here we've got at least 5 rufous dolphins passing through the area. Here's the same plot again, and in the center in the purple we have a single harbor porpoise quick train. Although we couldn't localize between the clusters, we could check for click matches between the clusters. And lots of click matches and minimal clock drift between the clusters is critical for successful localization. So we looked at a random sample of quick trains marked on cluster 1 and compared them to clicks detected on working channels on cluster 2. And we found high percentages of mean click matches within 1 second for all species. This suggests that the potential for successful localization when all channels are functioning is high. So in conclusion, a compact PAM system and methodology has been developed to monitor cetaceans around a utility-scale tidal cut. We've had some teething problems, but assessment suggests that the system is fit for purpose. The multi-channel system is now being updated and will be redeployed summer 2020 with mooring modifications. And we experienced moderate dolphin encounter rates with porpoises to be confirmed, so this gives us a real opportunity to study dolphin response and the potential collision risk. I'd like to thank the funders, co-authors, and their collaborators. Thank you very much.
That was great, Gemma. Thank you so much. One quick question, then I think we'll try to open up questions to everybody. Gemma, the question is, are there concerns about harbor seals in the area of the Kite, and what are the plans to monitor for these animals?
No, so harbor seals are pretty rare in Wales, so they weren't one of the species of concern for this development. There are grey seals in the area, but they occur in really high numbers. So it was just cetaceans that we were monitoring, and cetaceans that regulators felt were the key species in question.
Okay, thanks so much. I think we are going to look at some questions that have come in for a number of people. Now, I just realized I'm sharing my screen and I can't see the questions. Jen, can you take a look at those?
Yeah, no problem. So going back to some of the questions we missed earlier on, Kate, there were a couple of questions for you that we didn't have time to get to. There's one here from Carol. Really interesting results. Fish-based behavior could explain Doug's porpoise results. We look forward to the quantitative analysis on occurrence on the video. My question is, the passive acoustic monitoring data recently collected at MAGED indicated that porpoise occurrence was significantly higher during the night, and this has also been seen at a number of other sites. An obvious limitation of the vantage point surveys and underwater cameras is that data can only be collected during the day. Has that been considered in your work validating the prediction of collision risk?
Yeah, that's a really good point, actually. And, you know, when we were first discussing the approach to environmental monitoring up in Shetland, the regulatory and advisory body sort of agreed that the approach based on subsea video was enough to meet the requirements of the licenses for the project. But yeah, as the evidence base has grown, not only around our project, but some of the others that we've heard about, you know, it's apparent that the lack of nighttime monitoring is potentially, you know, we're missing a piece in the jigsaw, really. So yeah, we are looking now at supplementing the sort of existing techniques with acoustic instrumentation, a bit more like some of the other techniques that we've heard about in some of the other talks today, to sort of not only gather information during sort of nighttime operations, but also cross-validate a little bit between all the different methodologies to just build confidence really in all the different approaches and when they may and may not be suitable. And I think, you know, something that sort of strikes me from a lot of these talks today is there's no single approach that you can take to gathering sort of evidence required to sort of fully understand how wildlife interact with operational turbines. It's a bit like sort of bits of a jigsaw, and you sort of fill in the bits that you can in the best way you can. But yeah, for sure, we're now looking to integrate some acoustic techniques up in Shetland to fill in another bit of the jigsaw that's missing for us.
Great, thank you, Kate. I'll jump around a little bit here to make sure that we cover some of the questions for all of our speakers. There's a question here for Craig. There looked to be some quite high frequency components in turbine noise. Can you comment on potential audible distance and potential for behavioral responses for harbour porpoises?
I think that would be beyond my ability to do that. It's certainly something that we have those conversations between JASCO, who does the analysis, and the engineers as far as the cause of those noises and that sort of thing. But certainly if you wanted to send me an email, we can explore it further.
Yeah, no problem. We'll keep a record of the questions, Craig, so we can share that one by an email to you if you want to consult with your team. And question for Diane, are there any fisheries interactions with the cable?
Is there any interaction, fish interactions with the cable? Well, actually, we are not. We don't have any camera or things like that looking at the cable. But the cable is sitting on the seabed, so we assume that there is no interaction. We have not observed anything, any trace or anything on the cable so far. And then that's why also we are doing electromagnetic measurements on the cable, because I think this is the only impact that that could appear with the cables, and that's what we are going to check.
Okay, great. Thanks, Diane. A question for Gemma, or indeed for any of the speakers. It seems that all of these deployments have fairly extensive environmental monitoring. Was this monitoring elective, mandated by regulators?
I'm happy to answer that. In the Maygen case, it's Douglas Gillespie here. This whole monitoring program was very carefully coordinated with the regulators. So, yes, it is mandatory.
Thanks, Doug. Would anyone else like to come in on that question?
Yeah, Kate here from Nova. Same here. The license conditions that we have to adhere to throughout our operations dictate certain things that have to be carried out in terms of environmental monitoring, but the way that we address that is sort of open to negotiation with the regulatory bodies and their advisors. But yeah, it's a fine balance really for developers. You know, I think all of us probably have always got a weather eye to the future and trying to sort of understand not only what we need to do to discharge license conditions and meet the regulatory requirements, but also what evidence is going to help us de-risk our future projects. So I think, you know, all of us have that in mind when we're thinking about designing our environmental monitoring.
Fraser here from Maygen. So no, it's Fraser here from Maygen. I kind of second that. We've had our requirements for the regulators for our current consent in phase 1A. I think those conditions are actually coming to an end now, and we're managing to close some of those out. But we are now actively investing in the next round of environmental monitoring to close some of the gaps which we identified in the initial monitoring phase. And that is really looking towards the future. So we are now putting our own hand in our own pocket to push this forwards for ourselves and also for the industry.
Thanks, Fraser.
Same in Wales, yeah, it was a license condition to monitor cetaceans during operation, but the methods of which was kind of an R&D development, and we formed an advisory group with the regulators, with UNESCO and the university, and sort of a work in progress, so we could try and learn as much as possible during that time.
Great, thanks for that, Gemma. Okay, moving on to another question here. We've got a question for Kate from Ellie Goodfellow. Really interesting presentation, thanks for that. I'd like to know, do you have pre-operational data for this area which you could use for comparison? If so, what changes do you see?
Yeah, we've got, so the Vantage Point surveys that I talked about started in November 2010, and the first turbine, the 30 kilowatt prototype, didn't go in the water until 2013. So we've certainly got plenty of pre-deployment Vantage Point data. We obviously don't have any subsea video footage before turbines went in, because the turbines themselves are the platform on which the subsea video cameras are mounted. And certainly, you know, we are looking at whether there's anything that we can do in terms of sort of before-after impact type comparisons with the vantage point data. What I would say is, getting back to my point about the sort of zero dominance of that data, there's a lot of zeros, ones, and not many big numbers involved in data sets where you're sort of looking at gathering land-based observations of birds and mammals in these areas, or certainly not for our site. So that does carry with it statistical limitations with what you can do with that data. And I think, you know, that to me really emphasises the point of being realistic when you're designing these monitoring programs as to what you can actually do with the data that you're gathering, and be sort of really clear up front about the objectives and what it is that you're wanting to monitor, how you're going to do it, and what type of analysis is realistically going to be possible with the data that you're gathering. Because, you know, these encounters between wildlife and operational devices, they're really rare. They're rare events. I think that's another message that's come out to me from all of the presentations. So it's quite hard doing statistical analysis on that type of data where it's really sort of a very occasional interesting observation. But yeah, for sure, we are going to be looking at trying to determine the power of our data to get sort of before after type impact.
Great. And a follow-up to that one on the data analysis side of things, did you analyze the 20,000 hours of video manually, or do you have an automated method?
Good question. At the moment, we have no clever algorithm for separating a flappy bit of seaweed from a cormorant or a harbour seal or a fish. We're making progress with that. We're working on that, and we're trying to come up with slightly more clever ways of sampling from that 20,000 hours of footage. But for now, what we've tried to do is come up with a sort of an intelligent sampling protocol. We've got the benefit of having the land-based observations, so we know from that times when there may be higher numbers of birds and mammals interacting with the array area, so we can use that to inform a sort of a stratified, intelligent approach to sampling from that 20,000 hours of footage. And we've also taken a sort of a random approach as well, so that we're not sort of biasing the approach to sampling. But no, at the moment, that processing is done in a sort of fairly manual way.
Okay, thanks for that, Paige. Another question here for Craig from Matthew Baker. How would you expect the results of the monitoring to vary seasonally and annually? What can you infer about the underwater video footage results with respect to environmental effects of turbine operation, of fish presence, abundance, and behavior?
The data we've collected so far has been from the spring of last year and fall, where we saw similar patterns, I guess, or really very little activity, very few observations of animals other than the jellyfish. So I think we need to keep collecting data to sort of flesh out that picture. And I've forgotten the second part of the question.
The second part of the question was, what can you infer about the underwater video footage results so far with respect to the environmental effects of turbine operation on fish presence, abundance, and behavior?
Right. Well, I guess the limited amount of observations said something. Again, there needs to be more data, as I think the industry recognized, before any conclusions are drawn. But we're starting to see through, I think, a lot of these presentations a trend that there doesn't tend to be a lot of activity, and so we'll keep collecting the data and be able to make more meaningful inferences in the future.
Great, thanks, Craig. I've got one final question here on my list for Kate from Matthew Baker. With respect to fish, are these observations what you expected? Were you expecting to observe other fish species during monitoring? And in that case, why or why not?
I think in terms of what species may or may not be present up in the site at Blue Mole Sound, then certainly, you know, we would expect other species to be present. I think, you know, when you sort of look at the type of data that we're all gathering, I think it sort of it helps to sort of think like a fish, or think like a diving bird, or think like a mammal, and think about, you know, how you may or may not use these sites, and therefore whether sort of what we're all observing in our environmental monitoring programs sort of make sense from an ecological and an energetics and that point of view. So I haven't been surprised really by the results that we've seen, that really the types of, you know, the fish that we're seeing are a species that typically tends to school around devices underwater. You know, the pollock family, that is the species that we're seeing, tend to you know, habit underwater structures, artificial reefs, wrecks, and I think that's just how our turbine is acting as a fish aggregating device, basically. And that's what we're seeing. And I think other species that may or may not be in the site are using the sort of habitat, the tidal habitat of Blue Mole Sound in a different way. So although they may be present in the wider area, they're sort of from an ecological or an energetics point of view, they've got no reason to be inhabiting the area that our turbines are located in, and particularly at a time when the tide is running. So that, from that point of view, I'm not surprised particularly.
Great, thank you, Kate. That's all the questions that I have for now, and we're getting pretty close to time, so I'll hand back over to you, Andrea.
And finally, I just want to say we are really interested in hearing from you. There isn't much time now, but whether this was useful, we'd really like to hold another of these forums in the next 2 to 6 months, assuming there's interest. And we, once we get through a lot of presentations, we may have more time for discussion. If you have topics of interest, if you want to put them in the chat box now, or send an email to Dorian Overhoos at pnnl.gov, that would be really great to know what your interests are, and particularly, do you have speakers you can suggest? So please get back to us, or to any of us who've been on this webinar. So at this point, I don't want to take any more time to say thank you very much from us at PNNL, especially with my team, Dori Overhoos, Lanae Hemmering, and also Jen Fox and the whole team at Aquaterra. And especially a big thanks to our, thank you very much. We do plan on mounting most of these presentations on TSIS in the next couple of weeks. You will get presentations and audio of the presentation and the Q&A if they are available. Okay, with that, I want to conclude this webinar and thank you very much for joining us.